Okay, so first of all, the last unit talked about the 5 types of chemical reactions. We talked about combination, decomposition, single replacement, double replacement, and combustion. And then we also talked about acid and base reactions in there a little bit, which are kind of like a double replacement reaction, but we always get water as a product, right? This unit is kind of like a subunit of that. We're actually going to focus on just acid-base reactions, and then we're also going to learn a new type of reaction called redox reactions. Okay. So first of all, before we can do all of that, we need to review the parts of solution. So, does anyone remember what a solution is? What type of mixture? It is a homogeneous mixture. Does anyone remember what the solute is? What is being dissolved? What gets dissolved? Does anyone remember what the solvent is? What is doing the dissolving? What is the solute is being dissolved in? Does anyone remember what soluble means?
Whether it can dissolve in water.
Right, we just talked about solubility. So soluble is can it be dissolved? Miscible means it's talking about when we have two liquids that can dissolve in each other. So if you take, has anyone ever made like gravy before, and sometimes you will take like flour and dissolve it in water first, and then you take the flour water and you make the gravy out of it. You mix the two liquids together. That's something called miscible. Okay. So does anyone know the next word that I added onto yours was immiscible? So if miscible means two liquids can dissolve in each other, what do you think immiscible means?
They can't dissolve in
They can two liquids that cannot dissolve in each other. Can anyone think of an example?
the oil.
Oil and water. Does vinegar and water
Like
mix those
salad
together? Do what? Salad dressings. A lot of salad dressings are liquids that won't mix together because a lot of salad dressings have oil in them. Okay, so next we're going to learn about aqueous solutions, which we've been talking about a lot, right? We've been talking about what aqueous solutions and our acid-base, but we really haven't focused exactly what aqueous is. Aqueous solutions means that you have something that is dissolved in water. Water is a very, very, very good solvent. Why is it a very good solvent? Because it's polar. Okay, and we're actually going to look at a water molecule and we're going to kind of discuss all of these things. First of all, if we look at our oxygen molecule that we see here, we see that oxygen has it's going to have a slight positive charge. If we look at the way it is shaped, we can see that it's actually called a bent shape because those angles look bent, right? Doesn't it look like we took it from being straight and we bent it? That's why it's called the bent shape. And so if you look at it, oxygen has how many valence electrons? 6. So we're probably going to have an electron here. We're going to have another pair here. There's 2, 4, 5, 6, 7, 8 are with the bonds. So now we have, and if you look, what kind of charge do you think we're going to have on oxygen with all those electrons? This end is going to be slightly negative. What kind of charge do you think the hydrogens are going to have then? They're going to be slightly positive. Okay, and if you notice, it has this bent shape. Usually, atoms that are arranged like this go straight up and down, right? Water was a special case that I made you guys memorize in general chemistry, right? It didn't fit the rules. Usually they go straight up and down, but this one is bent, which is what gives water all of its special characteristics. This has a bond angle of 105 instead of 180. If it was 180 bond angle, we wouldn't be polar because our polarity would cancel out, right? But since it's not straight up and down, since it has less than 180, it gives us these slight positives, slight negatives, which basically makes the right end of this picture negative and the left end positive, right? The distance between the two bonds. All right, so now let's talk about hydration just a little bit. Hydration, which we've talked about hydrates before, right? What is hydrate? What are hydrates? Compounds that contain water mixed in with them, correct? Okay, well, hydration is the process of breaking the ions of salts apart. So, for instance, if we have sodium chloride, this process is when we break it apart and we get sodium with a +1 charge and chlorine with a -1 charge. Ions have charges that attract the opposite charges of the water molecules. So I just showed you what a water molecule looks like. So the positive sodium is going to be attracted to the negative oxygen. The negative chlorine is going to be attracted to the positive hydrogen. So they will just continue to arrange themselves so that they will be trying to make themselves neutral. All right, so let's look at a nice pretty picture. Here we have an undissolved salt. We can see that we have positive and negative charges all mixed in there. Let's pretend it's sodium chloride. We all know what salt is. If we take a water molecule, okay, we can see that we have positive ends, we have negative ends, which the positive and negatives are all actually on the wrong side. Awesome. But I don't know how to change pictures. So basically what's going to happen is all our hydrogens are slightly positively charged. So what's going to happen is these molecules are going to arrange themselves so that they fit with the positive. So as this starts to break up, the negative is going to come in here, and then the waters all arrange themselves so the positives are towards the negatives because the negatives are towards each other, right? Hydrogens are slightly positive. So if we keep going, if we have a positive charge then, the waters kind of arrange themselves so the negative is towards the positive charge. So then over here is probably going to be a negative, and here's going to be a negative, 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 and they just keep arranging themselves. This is how things dissolve in water. Okay, solubility is how much of a substance will dissolve in a given amount of water. Okay, usually when we're talking about solubility, we're talking about grams in 100 milliliters of water, or there's that word molar comes into account again, which we did do a little bit in general chemistry, but we aren't great at it, so we're going to be doing that a little bit more today. Solubility varies greatly, but if they do dissolve the ions, they are separated or hydrated. So if something will dissolve, you break apart the ions, and it arranges itself like the picture I just showed you. Okay, once you break apart the ions, they are free to move around. Okay, they move around constantly, they do not stop. This is how electricity works. Electricity, you break apart, and the electrons are allowed to move freely. So whenever things are allowed to move around freely is when you get all of these properties, dissolving, solubility, electricity, all of these things kind of go hand in hand. Okay, water can dissolve non-ionic compounds if they have polar bonds. So, for instance, sugar is not an ionic compound, but does sugar dissolve in water? Yes, so what does that tell you? It has to have polar bonds in it. Okay. So water will always dissolve ionic compounds, but it will dissolve covalent compounds if they have polar bonds. Okay, how do we determine if something has a polar bond? But how do we determine that? But don't we have to draw it out? Oftentimes, in order to determine if something's polar, you have to draw its structure, because sometimes the polar bonds will cancel each other out, right? So we need to, if we don't remember how to draw it, we need to get a little bit better at that. Okay, electrolytes. One thing you guys love so much. Okay, electrolytes are often, when we're dealing with electricity, electricity is when our charges are moving. Only ions that are dissolved can move, so solid salt is not going to move around, but if we dissolve it into water, it is now able to move around. Compounds that conduct an electrical current in an aqueous solution or a molten compound are called electrolytes.
Are these like same kind of electrolytes as Gatorade? No.
Well, kind of. The electrolytes in Gatorade, I mean, the reason they're called electrolytes is because there's stuff dissolved in there, but it's different. Don't think of them as the same thing, because I think you'll get confused. It's not that they're not the same thing, it's just, it's a stretch to make them all fit under the word electrolyte. Okay, so first of all, we can classify our solutions in 3 ways. So we are going to classify the first one as a strong electrolyte. Strong electrolytes means they can completely disassociate. Disassociate means you can break them up into their ions. Okay, these ions are very good conductors. So strong electrolytes will completely break apart. They will every single one of them that are in the solution will break apart into their ions, and there will be no compound left. Okay. The opposite is something called a weak electrolyte. This is only a certain fraction will dissolve into ions. So some of it will dissolve, but not all of it, because its electronegativity probably isn't very high or very low, so it's going to kind of dissolve, but not all the way. Okay, few ions. It's still going to conduct electricity, but not as well. And then we have something called non-electrolytes. These do not break apart at all. So if we have no ions, we are not going to be able to conduct electricity. So we have strong electrolytes completely break apart, weak electrolytes kind of break apart, and then we have non-electrolytes that won't break apart at all. Okay, solubility rules assist in determining if something will be an electrolyte or not. So last year when we did electrolytes, I made you guys identify strong versus weak by just looking to see if it was polar or not, right? But now we know our solubility rules, so we really can identify if something is soluble or not and how strong of an electrolyte it's going to be. So if you have those that have, let's see, is that a slide? Those elements that are bonded to like alkali metals, those are always soluble, right? Usually our alkali metals are always soluble. Remember those solubility rules? Our nitrates, our chlorides, those were, for the most part, always soluble, right? Okay, those are going to be your strong electrolytes. Our weak electrolytes were, like silver chloride, that isn't always soluble, right? Some others would be like sulfate. Sulfates were sometimes soluble. Those guys that are sometimes soluble, those are going to be your weak electrolytes. And then the ones that have the X in the boxes that are never soluble, those are going to be your non-electrolytes. Now that we know our solubility rules, we can kind of start to identify these a little bit better. So types of electrolyte solutions, first of all, is an acid. We have already talked about this a little bit, but acids have to form hydrogen ions when you dissolve them. So right off the bat, how to identify something as an acid? It has a hydrogen, okay? Strong acids fall apart completely. So that means that like for instance, if we're dealing with sulfuric acid is a strong acid. It's going to disassociate completely, which means its two hydrogens are going to break apart from the sulfate always. When you dissolve it into water, it's going to always break apart. Okay? There are 8 strong acids that you guys need to start getting familiar with. These are going to always disassociate. These are always going to break apart into their ions. We have sulfuric acid, nitric acid, hydrochloric acid, hydrobromic acid, hydroiodic acid, periodic acid, chloric acid, and perchloric acid. So these are the 8 acids that are called strong acids, and these are always, 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 always going to disassociate.
What is the only strong acid?
Yes. All of the other ones are called weak acids, and they are going to be weak electrolytes. They're going to disassociate to some degree, but not completely. These guys will always completely disassociate.
We literally had a question about what we call an acid that dissolves completely when put in water. Last night I knew too. Like that was one of the questions we were like, we talked about this. And that was one of the they were talking about like strong acids and weak acids. But the answer was strong acid.
Did you get it right?
No, I have no idea.
Well, now you do.
Now I can tell Joe can I answer our question.
Okay, so weak acids don't disassociate completely. They will break apart to some degree, but not all the way. Okay, bases, which you've already talked about this, acids form hydrogen ions. Bases form hydroxide ions when you dissolve them in water. We have strong bases just like we have strong acids, okay? Strong bases completely break apart. And there are, again, There's 1, 2, 3, 4, 5. There are 8 of them as well. So first of all, the ones bonded with the alkali metals, this would be potassium hydroxide, sodium hydroxide, lithium hydroxide, cesium hydroxide, and rubidium hydroxide. These are your 5 of your strong bases. And again, sometimes this is hard to memorize. And I'm thinking that after we do this a few times, it'll become second nature. But hopefully we'll start picking up on patterns. Alkali metals are very soluble, right? So if something's bonded to an alkali metal in the base, we could probably assume it's a strong base, right? Some other ones that aren't with the alkali metals would be barium hydroxide, strontium hydroxide, and calcium hydroxide. So what type of metals are those guys? Those are alkaline earth metals, right? So if all else fails and we're trying to identify something as a strong base, look for alkali metals and alkaline earth metals, right? Because that's a pattern we can see. Now that doesn't include beryllium and magnesium, but we can kind of see a pattern, right? So if you're ever stuck on a test, think, okay, strong base, first 2 columns, okay. Okay, all other hydroxides are something called weak bases, and this includes NH3. NH3 is ammonia. Does it have hydroxide? No, but it's one of those things that doesn't follow the rules. We know ammonia is a base, right? Don't we use it to clean our house? Anything you use to clean, for the most part, is a base. Ammonia does not fit the hydroxide rule, but it still is a weak base. Okay, so up to this point, and last year, whenever we use solutions in the lab, didn't I make them for you? I made them for you. I had them up there. I would tell you their molarity. I would tell you how strong they were. From this point forward, I'm going to have you guys start making your own solutions. So before we can make our own solutions in lab, I have to teach you how to make solutions, right? Okay, this all has to do with something called molarity, okay, which we've learned before, but now we're going to kind of start to figure out how to do it all by ourselves. So when we're measuring solutions, the first thing we have to do is figure out what concentration. Concentration and molarity go hand in hand. They pretty much have the same definition. So concentration is when we're talking about how much is dissolved. And another word for that is molarity. To find your molarity, you take your moles of solute and you divide it by your liters of solution. And we abbreviate molarity with a capital M. That capital M is very important. If you put a lowercase m, it makes you think of meters, right? We're not talking about meters, we're talking about molarity. So you have to tell me that it's a capital M. Okay, 1 molar solution of anything. If I tell you I have 1 capital M, I am telling you that I have 1 mole of my solute dissolved into 1 liter of solution. So if in lab I tell you to make a 1 molar solution of sodium chloride, okay, you're going to take 1 mole of sodium chloride and you're going to dissolve it into 1 liter of water. 1 molar solution of sodium chloride. Okay? So let's do some practice. Now, up to this point, we have used the molarity. Just go moles divided by liters. It's an easy 3-variable equation, right? There is another way which I actually think is easier. I think it's easier to do it stoichiometry-wise because our units don't always match up, do they? Sometimes we're given molarity, sometimes we're given moles, sometimes we're given liters. As opposed to trying to fit it in the equation, sometimes it's easier to just do stoichiometry. So I'm going to show you how to do it that way. But if you guys want to plug it in, do conversion factors, mess with your numbers, and then plug it into the equation, I don't really care how you get to the answer as long as you get to the answer. Okay, so let's look at this one. Let's see if we can do it in the stoichiometry way. It says calculate the molarity of a solution with 34.6 grams of sodium chloride dissolved into 125 milliliters of solution. So I want molarity. Molarity is moles per liter, right? So I'm going to do stoichiometry. I always start with what's given to me in the problem. I'm going to start with 34.6 grams but I want my unit to be moles per liter, correct? So first of all, let's change this into moles, right? So, first conversion factor, 1 mole of sodium chloride has a mass of 58.53 grams. So now we're in moles. Yay. But we don't want moles. We want moles per liter. So is my volume going to go on the bottom or the top of this conversion factor? Bottom, because we want moles per liter. So we want our liters to be on the bottom. Well, we don't have liters. We have milliliters. So you put this on the bottom. But we don't want milliliters. So you have to get it out. And if you guys want to do this step in your head, go for it. If you just want to move your decimal over 3 times, I'm perfectly happy with that. Okay? But now our grams cancel out, our milliliters canceled out, and we are left with moles on the top and liters in the bottom, which is the correct unit for molarity, correct? So then you just do the math. You're going to do 34.6 divided by 58.53 divided by 125 times by 1,000, right? How many significant figures do I get to keep in my answer? 3. So, yep, because there's nothing to go on top of it. Because nothing goes there. What could we put there? You can put a 1 there, but timesing by 1 isn't. I don't care how you go about doing it. Yeah, as long as you get to the right answer. Because we're not always going to be given moles and liters. Sometimes we'll be given molarity and you have to change the unit. So there are lots of different ways to get to the right answer. I mean, you guys can just plug it into the equation if you prefer. I just wanted to show you that sometimes this way is actually easier, depending on what you're doing. Yes?
So, like, whatever the moles, like, you know, like, for the grams, you can divide that by 125.
Yes.
Okay, so that's what.
Yeah, I just go in order. So I would, in my calculator, I would do 34.6 divided by 58.53 equals divided by 125 equals times 1,000.
Oh, okay, so that one is really just whatever you want.
Yes.
Okay, that's what I thought. I thought you were saying, like,
Okay, so if I put all this in my calculator, I'm going to get an answer of how many significant figures, first of all? 3. So I'm going to get 4.73. And what's my unit? Capital M for moles per liter. So I have a 4.73 molar solution. And we're going to do several examples. Trying to get the hang of it. It's not that bad. Easier than limiting reactants, right? Okay, so molarity, capital M, again means we have moles of solute divided by our volume of solution in liters. Shorthand, moles, shorthand for moles is ml, liters is a capital L. So for instance, if I'm giving a 6 molar hydrochloric acid solution, to make this, I take 6 moles of hydrogen chloride and I dissolve it in 1 liter of whatever to get my 6 molar hydrochloric acid solution. So there are, but we're not always dealing with molarity. When we're dealing with this, sometimes we are talking about something called ion concentration. So when you take hydrochloric acid, to make it an acid, we know that it disassociates into hydrogen and chlorine, right? So sometimes you're going to be asked what the ion concentration is of a solution. So to figure this out, it's actually pretty easy. So for instance, if we have a 6 molar hydrochloric acid solution, we have 6 molar solution of hydrogen, and we have a 6 molar solution of chloride. It's a 1-to-1 ratio. We have 1 chlorine to 1 hydrogen, right? 1-to-1 ratio, so if we have 6 molar solution of hydrochloric acid, we have 6 molar ion concentration of hydrogen, 6 molar ion concentration of chlorine. But do you think we're always going to have a 1-to-1 ratio? No. So let's do this one. We have a 6 molar solution of sodium sulfate. Okay, sulfate is a polyatomic ion, so is it going to break apart? No, it's going to stay in its polyatomic ion. So this is going to break apart into sodium and sulfate, right? Well, we have twice as many sodiums as we do sulfates, correct? So we have one sulfate in our compound, so the molarity of that is not going to change. We're going to have 6 molar ion concentration of sulfate. What do you think it's going to be of sodium? 12, because there are twice as many sodiums in that compound. So we're going to have a 12 molar ion concentration of sodium.
So when we write that, sodium we don't keep in such that we just write in the number.
Right. Because the only reason sodium sulfate has a subscript is to make it in neutral. But when it's by itself, it's not going to be neutral, so we don't need a subscript anymore. Okay, so let's do another example. So this one says, how many moles of nitric acid are in a 2-liter solution that is 0.2 molar? So again, sometimes it's easier to do the dimensional analysis, the stoichiometry, right, than it is to try to plug it in. This is a perfect example because we aren't given moles and liters. We're given molarity, aren't we? So this is one of those times where it's actually easier, as opposed to trying to convert everything and then plug it in. Sometimes it's easier to just do stoichiometry, but again, I don't care which way you do it. So right off the bat, I'm going to start with my molarity. So I have a 0. Oops. I have a 0.200, and we know that molarity is what? Moles over liters, right? And I write it like that so I can do stoichiometry so I get my units to balance. We need to go to just moles. So I need to get my liters to cancel out. Luckily, it's in liters, so we don't even have to convert it. So is my 2 liter going to go on the top or the bottom? Top. Does anything go on the bottom? Nope. So my liters cancel. We're left with moles. So if I do 0.2 times 2, I'm going to get 0.400 to maintain significant figures. Moles of my solute, which is HNO3. I was just looking at the 0.2, but 2.0 has 2. These are easy, way better than combustion problems, right? Okay, so let's do this one. What volume of solution is necessary to provide 2 moles of nitric acid? So we're looking for volume. Does it give us a specific, do we have to be in milliliters, do we have to be in liters? Nope, it's not giving us a specific, so we can just, whatever we get to, whatever's the easiest. So I'm going to start with molarity. So we have 0.30 moles per liter, right? Okay, and we also are given 2 moles. So where am I going to put my 2 moles, top or bottom? Why am I going to put it on the bottom? So it'll cancel out. Does anything go on the top? Nope. Moles cancel. We have liters on the bottom. Anyone see a problem with that? It needs to be on the top. So we can either, once we get our answer, we can just do the reciprocal, 1 over that answer to put on the top, or we could have done this differently, and we could have done liters over 0.30 moles. We could have done it like this. Like I said, there are several ways to get to the right answer. I don't really care which way you do it, as long as you get to the right answer. So either way you do it, you should have gotten an answer of 6.7 liters. Since it wasn't specific on milliliters versus liter, I don't care what answer you give me. So I'm going to stop at liters, because that's easy. We don't need to do any more conversions, right? Okay, this one is the same basic concept, except this time it's asking us for mass, not molarity, not moles, not liters. It's asking us for mass, so we're going to have to do an extra step. So this one says how many grams are solute and present in 50 milliliters of a 0.360 molar solution. So I'm going to start with molarity again. So I'm going to do 0, 0.3. Oops. I switched apparently. Okay, 0.360 moles per liter. We gotta get the liters to cancel out. So do we want volume on top or bottom? Top, and I know that 50 milliliters is, right, I just moved the decimal over 3 times. That way I don't have to do another conversion factor. So that got rid of my liters, but we don't want liters, we want grams. So is the grams going to go on the top or the bottom? Grams. What's going to go on the bottom of this one? Moles. Okay, 1 mole of this compound has a mass of 294.2. So if you do 0.36 times 0.05 times 294.2, everything should cancel except for our grams, and you should get an answer of 5.30 grams. So to make this type of solution, we would have to measure out 5.30 grams, dilute it with water, and we're going to get this molarity of the solution. And I am going to make you guys make your own solutions this lab. Maybe not the whole year, but for this one for sure. Okay, this one is the same basic concept, except it's asking a little bit differently. It's asking for, it's giving us, I don't know, I feel like whenever we're giving polyatomic ions as both the cation and the anion, it kind of throws us for a loop. So let's do one like this. It says that 4.28 grams of ammonium sulfate is dissolved in enough water to form 300 milliliters of solution. What is the molarity of the solution? So how do I even start? Where should I start at? So I'm going to start with my 4.28 grams. We're wanting to go all the way to molarity. So first up, I need to convert this to moles. So 1 mole of ammonium sulfate, that's fun math, is going to have 132.15 grams. Okay, that cancels out our grams, but we don't want moles. We want moles per liter. So are my liters going to go on the top or the bottom? Bottom. And am I going to put 300 milliliters? What am I going to put? 0.3 liters, correct? Does everyone understand how I'm moving the decimal over 3 times? We can do that part in our head, right? Okay. Does anything go on the top? Nope. So I'm going to do 4.28 divided by 132.15 divided by 0.3, and I should get an answer of 0.1 molar solution, and I only get one significant figure because 300 only has one significant figure. Okay. I feel like we kind of get this, so I'm going to skip this example, unless you guys want me to do it. You want me to do this example? Why was that just one significant figure? Because 300 only have one significant figure. You guys want me to do this example? No? Okay. So this is how you actually go about making the solution. So first of all, these are flasks, but they're probably flasks that you've never seen before. You've probably never seen these types because I don't let my general chemistry kids touch them because they break really easily. But these are something called volumetric flasks, and they actually have a line on them about couple inches up on the neck, so usually there's like a line right here in this vicinity. And basically a volumetric flask is a flask that holds exactly 100 milliliters, or it holds exactly 500 milliliters, or there's some that are 1 liter. There are some that are different sizes, but our flask's very accurate, our beaker's very accurate. The line on these things has been measured to be exactly 100 milliliters or whatever the volume of that flask is. So if you fill it up to that point, you have exactly 1 liter of solution or 100 milliliters or whatever it is, whatever flask you're using. So that way it takes a little bit of the human error out. Okay, so basically what you're going to do is if we're making, like on that example we just did, we were making ammonium sulfate, right? So if I was wanting to make a 0.1 molar solution of that ammonium sulfate, like that example we just did, I'm going to measure out 4.28 grams of ammonium sulfate. It is a powder. I'm going to go to my scale. I'm going to use a weight load. I'm going to measure out 4.28 grams. And then what I'm going to do is I'm going to transfer it into the bottom of this flask. So I weigh it on the scale. I put it in the bottom of the flask. It's going to take up so much room. Then what you do is you add water until you get up to that line I was just talking about. In the process, you need to make sure that you have rinsed all the powder off of the neck. Sometimes those necks are really skinny, and so sometimes the powder, as you try to dump it down, will stick to the sides. So as you are squirting the water down in there, you need to make sure that you're getting all the powder washing out of the side. And of course, you think we're going to use tap water. Now we're going to use something called distilled water or deionized water, and basically it's pure water. It's not going to have all of the impurities in it. And it's going to be in the jugs. You guys have probably seen jugs of water in there before, right? So that's how you would go about actually making a solution. So let's see if we can. Okay, so let's do this one. It says, how many grams of hydrochloric acid would be required to make 50 milliliters of a 2.7 molar solution? So yes, we're going to do the molarity. We're going to figure this out, but then we're also going to talk about how we would actually go about making this solution. So first of all, we have to figure out how many grams we have to weigh to make the solution, right? So we're going to take the 2.4 or the 2.7 milliliters, 2.7 molar, so moles per liter, and I got to get this all the way to grams, right? To get rid of my liters, it gave us that we had 500 milliliters, so that's going to, or not 500, 50 milliliters, so that's going to go on the top. Okay, but we don't want moles, we want grams. So 1 mole of the solution is going to have a mass of 36.46 grams. The liters cancel out, the moles cancel out, we're left with grams. So if we do all of this fun math, we're going to get an answer of 4.9 grams of hydrochloric acid. So now we know the math, we've done the math behind it, but we're not done yet. We haven't even started to make the solution, right? So what would I do? How would I make the solution? You're going to go in there, you're going to get your hydrogen chloride probably, it's not hydrochloric acid yet. You're going to get hydrogen chloride, you're going to go and you're going to weigh out 4.9 grams of it. Then what are you going to do? How big of a flask? Okay, how many grams of hydrochloric acid? So, we probably don't have a 50 milliliter flask. We might. Let's pretend we have a 50 milliliter flask. So we're going to go find a 50 milliliter volumetric flask, right? We are going to put in our flask the 4.9 grams. Then what are we going to do? Add what kind of water? Distilled water until we get to the line. Now, that is the basic process, but is everyone listening? Okay, acids are kind of dangerous. Okay. Now, whenever you add water to hydrogen chloride, it's going to make an acid. Acids release a lot of heat, so that would get really, 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 really hot. So basically what you would want to do instead, this time we're going to change our procedure. So whenever you're trying to make an acid, what you want to do is you want to put a little bit of water in your volumetric flask first. So as you add the hydrogen chloride, the water can absorb the heat, so you won't break your volumetric flask. Because heat sometimes will start to shatter if it gets too hot too fast. Okay? So what you do is you add a little bit of water in the bottom of it, then you add the powder, then you finish filling it up. So you don't want to fill all the way up to the line, because then as you add powder, it's going to go over the line. But you want to put, I don't know, I'd fill it maybe 25% of the way with water. Add your powder, then fill the rest of it up with water. So on your paper, I need everybody to write this somewhere. You always add an acid to water. You never add water to an acid. You always add acid to water. So if you guys are making an acidic solution, you are always going to add your acid to water. Everybody write that down? Put stars and circles around it so you don't forget. Okay, we're going to talk about one more thing, and then I'll let you guys go and break. But it's something called dilutions. Okay, so sometimes you'll be given a solution, like for instance when I buy hydrochloric acid from my supply company, it comes in as 12 molar. Do you think I want to give you a 12 molar solution of hydrochloric acid? Probably not. So we have to do something called diluting it. Sometimes in the lab I have a whole shelf in there or the solutions are already made. And there's no sense in making another solution if I have a solution already and I can just dilute it a little bit down further to make it work for what I want. So it's something called dilutions. When we dilute something, you take your molarity times your volume of whatever you currently have, and then it has to equal your molarity and your volume of the dilution you're trying to make. So what you start with equals what you have to end with. It'll be different ratios, but it should be all equal to each other. This shows the number of moles in each solution, and they have to be equal. So let's do an example of this one. It says that a lab requires 500 milliliters of a 3 molar hydrochloric acid solution. How many milliliters of 12 molar HCl is needed to make the solution? Before we start this problem, we know that molarity is moles divided by liters, right? But we're given 500 milliliters and it's asking for milliliters. Do we have to convert that to liters? No. Why do we not have to convert that to liters? Because the molarities are going to cancel each other out and the volumes are going to cancel each other out. So as long as your molarities are in the same unit and your volumes are in the same unit, you don't have to do any converting. Okay? So basically, we're going to RMB equals RMB. A lab requires 500 milliliters of a 3 molar hydrochloric acid, and we're starting with our 12 molar, correct? So is the 12 molar going to go on the left or the right? Left. So I'm going to do 12 times my volume, because I don't know what that is, and we need to make our 3 molar solution 500 milliliters. So we have 12 molar hydrochloric acid solution. Well, we don't need 12 molar. I need 500 milliliters of my 3 molar. So I need to know how much of my 12 molar solution I'm going to dilute. So if you do 3 times 500 and then divide it by 12, we're going to get our volume to equal 125 milliliters. So basically what this means is I'm going to take 125 milliliters of my 12 molar solution. I'm going to put it in my volumetric class, and I'm going to add water until I get to where? 500. So I'm still using a volumetric class, but I'm going to show you a nice pretty picture. Oh wait, what? Okay, so let's pretend this is the problem we just did. We have our stock solution, that would be our 12 molar. We have our stock solution, this is our 12 molar. And we want it to be 3 molar, and we want it to be 500 milliliters. Well, we just found that we need 125, correct? So that's all the work that we just found. So basically what we're going to do is we're going to take this 125 milliliters, we're going to put it in a volumetric class, and we're going to add water until we get to our volume. Easy enough, right? Okay, but there is something that we have never seen before, and so I'm going to explain what it is. So if you guys look at this picture, you can see this odd looking item right here. Have you ever seen one of those before?
No.
No. This is called a pipette. Okay, pipettes. They actually take a little bit of practice in using, and I'm actually going to take you guys in the lab tomorrow and just let you guys practice using them. Okay, see if we can figure out how to use them. But basically, just like these volumetric flasks are exactly 100 milliliters or exactly 500 milliliters, it takes the human error out of it. Takes the human error out of reading the meniscus line and getting level and all of that fun stuff, right? Pipettes do the exact same thing, except they are. You guys know when we use droppers? Can we do that very exact? No. This is basically taking the place of using a dropper, especially when we're trying to do really small volumes. So sometimes you'll do a volume of 5 milliliters. Well, first of all, our graduated cylinders aren't that great. Secondly, droppers are not really very accurate. So we can use something called a pipette. And basically what you do is you, as we see in this picture, we're trying to dilute the solution. So they stick a pipette down. Maybe this is our 12 molar solution that we were just talking about. You stick the pipette in there, and there's actually a bulb that you put up at the top. You squeeze it, and then as it goes, it sucks the liquid up the top too. And there's a line up here, just like the volumetric flask. Once you get to that line, it's exactly, this is 25 milliliters. So once you get to that line, it's exactly 25 milliliters. And then what you do is put your finger over the top, like you do a straw, right? And you take it out of this one, and you put it in this one, you let your finger go, and all the solution goes on this side. But it's exactly 25 milliliters, so it takes out a lot of the human error. Then what you do is you add water to this line, and notice it's still blue, but it's not as blue because it is diluted. And I think I'm gonna take you guys in the lab and have you practice using this tomorrow because it does take some talent just to learn how to use it. Yes. Okay. Okay, let's not talk about it right now. Okay. Okay, so there is one more example. It says a 25 milliliters of water is added to 125 milliliters of a 0.15 molar sodium hydroxide solution. What will the molarity be of the diluted solution? So we have I always do that. Okay, so we have 125 milliliters of our 0.15 molar solution. Now, why did I underline some and circle others? To identify which is going with which. So we're going to be using the MB equals MB. Is my 125 and 0.15 going to go on the left or the right? The left, because that's what we're starting with. We're going to dilute that, right? So I'm going to take my 0.15 and I'm going to times it by my 125. And that has to equal, we don't know what our molarity is yet, right? And it has to equal our final volume. Do I put 25 milliliters here?
No,
It says, if you read it, it says 25 milliliters is added to 125 milliliters. So our final volume is not going to be 25, it's going to be 150. To get molarity by itself, you divide each side by 150, which gives us a molarity of 0.125. So my suggestion to you, these problems are not hard, much easier than the ones we've done in the last couple of units. But you need to make sure you're following your units. You need to make sure you read the problem, you understand what the problem's asking you to solve for. You understand that sometimes it's added. Okay, so when you see that word added, you need to go, okay, I'm gonna have to add two numbers together. You need to make sure you're reading the problem. Don't make this is easy, but you still have to be, sometimes when things are easier, we skip things and we overlook things and we don't pay attention. So make sure you're paying attention, okay? All right, so we're done with notes. I'm gonna let you guys take a break. Let's be back at 9:10, and then we'll do a little bit of practice.